So today we're going to prove that the brute force search algorithm that we saw last time, Grover's algorithm, is optimal up to the constant factor in the number of times that we have to apply gates, unitary operators, to the initial state to get into a state that we can measure with a high probability and discover the answer. So let's just go over what we had. So we're actually kind of for a moment thinking in terms of f being a function from 0, 1 to the n to 0, 1. And we saw that we could construct an oracle on this. So that would be, O would be a map which should take an element in a computational basis to -1 to the f of x. We can do that right now. Into the minus f of x. And we did that by means of setting up a unitary transformation UF, which took x, y to, so this y is just a single qubit, so this is just a single qubit, to x, y plus f of x, modulo 2. And then we noticed that if we apply UF to x and the minus state, 0 minus 1 divided by root 2 state, then this would go to -1 to the f of x minus. Thus, if we just forget about the minus, because it doesn't change any so long, we simply have this oracle which maps the x to -1/5 x of x. Now, we can think of this f as maybe this is a classical circuit which has got n inputs and it outputs 0 and 1. And one of the classical problems, in fact, an NP-complete problem, is to discover if this circuit is satisfiable. Is there an x such that f of x is equal to 1? Okay, so what we'd like to see is, let's imagine that we know what's next, and let's see if we can construct, and what we're going to do is construct an algorithm which allows us to find this x, okay, without having to go through all 2 to the n values, computing f each time to discover the x such that f of x equals 1. So let's suppose there's a unique x such that f of x is equal to 1. So by brute force, we would need to calculate 2 to the n values of to discover x, y, suppose. I suppose it's 2 to the n minus 1, because if it's do the first 2 to the n minus 1 or zeros, then you know it's the last one. But you know what I mean. So it's 2 to the n. And we saw that in Grover's, so Grover's algorithm allowed a square root speed up to some constant times 2 to the n divided by 2. Explicitly in this case, let's see what it was, because it was 2k plus 1, so it's k iteration where 2k plus 1 was equal to pi. So 2k by 1 theta is equal to pi, where the sine of theta divided by 2 was, in this case, the square root of 1 divided by n. So this in here is always going to be the 2 to the n. Okay, so since this is very big, this is very small, we have sine of theta divided by 2 is approximately just theta divided by 2. So when we now substitute, so we have theta y2 is roughly 1 upon n, this implies that 2k plus 1 is approximately pi. So car k is some constant times 2 to the n divided by 2. Now, and that was Grover's algorithm, but maybe there's a better way of doing this. And what we're going to try and prove first today is that, at least with a brute force search, we can't do any better. Okay, so that's the plan for the first part of today. Because of course, what we'd really like is that that this square root speed up would be something like a logarithm speed up. And then, if that were the case, then anything that we, for example, that was in NP, since we could check the solutions in polynomial time, we could from an exponentially reduce it down to simply going through all the, well, this problem, for example, we could then go through all the different values of that. If it was a exponential speed up, then suddenly this would become polynomial. So in a way, this is bad news, but it just means that what it means is we have to be more comfortable in our algorithmic development, that we can't simply do this brute force. Maybe there's still, well, as we were saying, we're going to make some assumptions. So we suppose our algorithm starts, our initial state is die. And then we apply unitary operations U1 to UK. Well, let's interjecting the oracle between each. Yeah. And you are just one. Okay, so this will lead us to arrive at the state. Let's call it psi. I'll put the k up on there. K x, where x indicates the unique value for f of x equals 1. Okay, so that's the x. K is the number of steps we're going to do, and we're starting with the initial step. Then we let's see if I can mix it up here, otherwise I'm bound to. So we go apply one, apply the oracle, apply U2, apply the oracle, just like we did in Grover's algorithm. So in fact, let's just recall what we did in Grover's algorithm. So in Grover's algorithm, the UK was always equal to twice this. That's a different state, map state. Yeah. Let's see. Don't really use last one. Okay, so it was the alpha was the state which was the perfect superposition, applying Hadamard's to all the quantum wires, and we just went forth backwards. We applied this, and then the oracle, and boom, 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 and it reflected like this to get us near to the beta axis. I shouldn't use alpha then because that was. Let's call this, just call this 5 more or something like that. And then we can use this as a normal file that we did last. Okay, so we want to calculate K. We want to bound K such that, assuming K is that this, when we measure with respect to x, so x, this is at least a half constant. Yeah, let's say we're going to call this. Okay, so we go back, we've got these U1s and UKs, and we could choose anywhere we like. They don't depend on X, but the oracle depends on X. So that depends. In such a way that we can then get to a state 5kx that when we measure with respect to the computational basis, we get x with probability greater than half. Okay, so that would be good enough for us to be able to find x by repeating the algorithm if necessary until we get sure ourselves that we can indeed deduce which x is the x such that f of x is equal to 1. Now our plan, we all have plans, so we can use the plan. Okay. Well, we want to prove, let's say we want to prove K is bigger than some constant root x. So essentially we cannot do better than Grover's. Okay, so we're going to do this with two lemmas. The first lemma doesn't actually use this fact. Yeah? So the idea is to look at this state, which is the state you would get, so 5k being the state you would get just by applying the unitaries. to the initial circuit. So here we've got phi x of k, that's interjecting the oracle between all unities, and this one is simply you don't use the oracle. And what we want to do is bound this thing, which is the sum over x norm of the differences between this one and this one. Okay? Now, it looks a bit strange to sum over x here because we've just said x is the unique value of f such that f of x is equal to 1. But then there's various f's here, so you can think of like we saw last time in the example with Grover's algorithm, we drew the oracle for each of the f of x's, if you remember. The one with f of x is 0 was 0, f of 0 was 1, the one with f of 1 is 1, f of f of 2 is 1, one with f of 3 is 1. You know, we saw where we kind of like the control properly things. So we did that last one, so we have one for each f, for each x. So that makes sense then to sum over that, and it's going to be that. Oops. Now let's just have a look before we start trying to bound this dk. So we'll bound dk in two ways and conclude this. Let's just see what happens when k is 1. So when k is 1, here we've. Do we do the oracle first then? Yeah, sorry, I'm missing oracle. Yeah, you do the oracle first. Yeah, so for your initial state, you apply the oracle to flip the sign of the x. So what would happen here if we had case? So here we just have u1, and here we have u1 oracle, the initial state. So if you think about that, all we've done then is we flipped the coefficient of the x, the amplitude of the x in the computational basis, and then we've applied u1 to this one and u1 to that one. Okay, so it's u1 to the difference of this and this, but the difference of this and this is just something times x. Okay, so applying the unitary doesn't change the length of that vector. So it's just going to be the flip of the sign. So there's a +1 to a -1, for example. That's going to be a 2. And then when we do this all squared, this thing is going to be at -4. So if k is 1, dk is at -4. So let's leave this up here for a moment because we'll need that. So our first level will be, I'm going to write it down here because I'm going to need to do a little bit of complex, I'm not saying complex analysis, but just a little bit of playing with complex numbers here at one point. Okay, so here we go. The first one we're going to prove is that this never gets more than 4k squared. So we just proved that for k is 1, but now we're going to prove this for k. So let's have a look. So the proof will be by induction. So by induction, k. And really, the base method would just be k is 0, right? I mean, k is 0 is also fine because this is just exactly the same things. So okay. So that one's fine. Let's just have a look at what this is. So note that this is going to be just UK plus 1 Oracle to X, and this one O plus 1. Okay, so let's have a look at dk plus 1. Dk plus 1 is the sum of x. So let's think, we've got this UK plus 1 here. That can come out of this one. And then we've got OX x minus. Okay. So it's the norm of that square. Now, use the user unitary operators. Yeah. So if the changing the applying the u doesn't change the norm of the vector. So this is essentially you can just forget about. Yeah, the norm of u. This is just the norm of this. Okay, so that's not going to affect the length of what we have there. So we can write this as the sum of x of the norm of OX. And now I want to put a 5k in here. So I've got to put that back in, plus O minus an identity of 5. Okay. Okay, so all I've done there is I've put in a OX, and I've taken away OX5 and added in OX5. Not really done very much. But now you see I'm almost getting to I'm almost getting the dx if I can get with this Oracle, which is also a unitary operator. So let me, do I need anything of this at the moment? Let me copy this one right here. Now, let's just do this. We've got a u plus b squared here. So let's just see where this goes. So this is u bar plus b bar dot u plus b, which is u plus now, here I've got some complex number z and its complex conjugate. So when I add up z plus z conjugate, I get twice the real part. Okay, so let's write this fixed working over here. This, let's say this is z plus z conjugate, which is twice the real part of z. So that's the next time will equal to twice the square, the norm of z, which is z conjugate. Okay, so if the real part of z is a, then this is just saying a is less than to the square root of a squared plus b squared. So this is, in fact, left equal to this plus twice the square root twice the norm u Uh, oh, of course, yeah. So it's twice the square root of u dot v. And now one more case, of course, when we see this, we instantly think of Cauchy-Schwarz. So this is then less than equal to u squared plus 2 u v plus v squared. Okay, so there's a very little calculation there, and now we can apply that to this. So basically, this is equal to, this is definitely equal to the norm of this square plus this square plus twice the norm of the things together. Okay, so that's all that has shown to us. So we can apply that here, and we get dk is less than equal to sum over x of ox now we'll get rid of that. And we're almost there, although I imagine slightly we're not, because now this oracle here, as a unitary operator. So again, it doesn't affect the norm of this vector. So we can just forget about this. And now this is dk squared. So we've got this is dk squared. So this should be dk plus 1. So this is dk. Okay, this is just dk. This ox minus 1, well, ox is precisely the identity minus twice x. Okay, because what the oracle does is it doesn't change things unless you're x and flips the sign of the x. So this is the oracle x. This ox minus 1 is basically just twice the k bra of x. So this implies that the norm of ox minus 1 of rk is the norm of twice so the norm of the x must be 1, so you just get twice 5k x. To this. So this is the formula. And then this final sum in the middle, well, that sum in the middle, we have real numbers here, ui's and vi's. So we know from let me get it up here. So well, let me write this down for you. X. Again, this ox can go because that's not necessary. So I just got here, I can put this, it's just going to be 2 times. Plus 4 times sum of the x of now again by equation 4 we have by the fact that this is the sum of so ui vi all squared is less than equal to the sum of ui square so ui squares sum of vi squared. So here this implies that this is less than the square root of this. Cauchy sort again. We can then split this up. So this is going to become the square root of dk, and this becomes the so this is of course sum over all x, just telling you the probability that x is 5k is x. This is just going to be 1, and likewise this one here. So putting all that together, we have that this implies dk plus 1 is less than to dk plus, so this is going to be 4 square root of dk plus 4. And since by induction dk is less than 4k squared, this is 4k squared plus 16k plus 4, which is 4. Except that it's not. Oh, sorry, 8 is square root. Okay. So it's 8. Yeah, so this is 2. This will be 2k. And that's it. So that's the end of that bridge. So that was the, let's say, well, I'm not sure that was particularly easy either. So that gives us the upper bound dk is at most 4k squared. So now to prove upper bound, it's very similar. We again start with dk, and here what we did was we interjected the terms. We moved a term and added dk plus 1s, and the simple trick now is going to work for the lower bound. Okay, so that's proves that this quantity doesn't grow too quickly, and now we're going to prove that if our k is such that the probability of measuring this 5kx with x is at least a half, then we must have that this is bigger than or equal to some constant times square root n. Okay, so sorry, times n. Of course, the square root comes from the fact that the other one is fixed. And that will be enough, yes, because then we have some 4k squared is bigger than some constant times. So that's what we have to prove. And the idea is similar to before. So we start off with taking doing another trick of in here, we're going to take away x and add it here. And then we're going to expand this thing as before. Now, we proved before that when we expanded this for the upper bound, we used the fact that the norm of u plus v squared was equivalent to the norm of u squared plus twice norm v plus the norm of v squared. And the bit where we use the upper bound on the z plus z bar, you can also use the lower bound, which would be bigger than minus twice the real part. And if you do that, then you'll get this squared minus twice. So now we get minus twice norm of plus okay, so that's doing exactly the same. This is my u, this is the v, and the u squared, this is now the minus, just switching this on in the same quantity we had last time. But now I've got the greater than here. And in exactly the same way, if I now define this quantity as, let's say, ek, and this quantity here as fk, then what I have is exactly this is greater than ek minus twice square root ek square root fk plus fk, which is square. So our plan will be to prove that this ek and fk square roots differ by something. No, I don't think I need that one anymore. So recall that this state is the one that we've ended up in, and so the only thing you have to remember is that this, if I measure it with respect to x, this thing. I don't think I need. This thing was bigger than 1/2. Okay, so let's see what ek looks like. I have ek is the sum of 5k x minus x. And when I expand this bracket here, then I'm going to get the bracket of 5kx and the bracket of x, which is going to be 2. And then here I'm going to get minus now at this point, they do a little cheat because here, this is just going to be 2 times n, something over every single state on a computational basis. And here, well, I want to prove they want to prove a lower bound on EK. Sorry, upper bound on EK. So what we want to prove here is that this is I'm remembering that space again. So let's see that. As it is. So this then gives. It then gives EK is less than or equal to 2n minus the sum over x. And what we're going to do is assume that this number is a real number. Now, that's because we could always replace x by e to the I phi x. So just go, x goes to e to the I theta x, sorry. And this doesn't change anything with respect to this still when we measure things, this isn't going to be there. But what it means is we can choose that theta so that these things are real. Okay, and so we just get twice x by kx. And we know that this is at least this 1 over the square root of 2. So this implies that this is 2n minus 2 divided square root 2 times n. So it's 2 minus. So that's a little bit of a cheat there. And finally, the same thing for f. So this f here, basically get the same things, but now with the phi k instead of the psi kx. So we have fk is twice 2n minus the sum of x phi k So if we sum in x here, this phi k doesn't depend on x. This is just j phi k. And as before, we could use our coding for and this is then bigger than 2n minus twice the square root of sorry, that was the same trick that we did before. Now we use Cauchy-Schwarz to get twice of the norm of j, norm of phi k. Well, the norm of phi k is 1, and the norm of j is the norm of j is with of square root of n. So here I have 2n minus 2 times the square root of n. So the square root of ek minus the square root of fk is, well, the square root of, well, okay, let's do the other way around. The square root of fk minus the square root of ek is something times n. Okay, because we've got 2n here, this is at least a 2n here, and this is less than equal to something less than 2n here. This is irrelevant. Because it's not of, well, for large enough n. And so we're there. So now we've done it. And so this implies, that square root of fk not square root of ek is at least some constant times square root of n. And since dk was bigger than, what was it 4 times? Yeah, I think that's bigger than. And so dk, which is bigger than the difference of that square, is bigger than some constant times n. So one of the exercises, which is probably the most difficult exercise, is to try and generalize this from f of x having exactly one solution to having m solutions. Okay, so it's going from, so in Grove's algorithm, that meant that instead of applying k, one divided, so it would be square root of n, it was square root of n divided by n. Okay, so where m is the number of times f is satisfied. Okay, so to finish our talk about algorithms, I wanted to just show you something. But we did talk a little bit about cryptography and the fact that with quantum algorithms, we are able to find feasible attacks on RSA and Diffie-Hellman and various other crypto systems as well. So the obvious thing to ask ourselves is if we can use quantum to improve our security and be secure against anybody who has their hands on a quantum computer. And so one of the simplest protocols is the BB84 protocol, which I want to mention now. And then after this, we'll be ready to move on to quantum error correction. And this protocol also kind of motivates quantum error correction, although the real thing with quantum error correction, as we shall see, is the fact that even every time you want to do anything on quantum circuits, you must always be able to protect it against any noise from the environment, which it will inevitably suffer. So we'll get to that shortly. But I want to talk first about the BB84 protocol, which goes along with quantum teleportation and superdense coding as one of the classics, because it's not too hard to get your hands on and to implement as well. So in many cases, we're talking about, in our algorithms, for example, we need hundreds of qubits, and as of yet, that's not implementable. But in the case of quantum teleportation, we just need a Bell step, and that's been verified. That's been done. And in the case of this protocol, it has also been verified a number of times. And in fact, if you look at the Wikipedia page from this, you'll see that there's been various successful implementations in the last couple of years. Yes, this is very much in the news, let's say. So the idea is the protocol allows Alice and Bob to share qubits prepared in the same states. Was communicating over public voltage. And the idea which an eavesdropper Eve access to but in such a way that Eve knows nothing. About the events. Okay, so you can imagine that it's really useful if you want to share a key, a number from which you're going to set your crypto system, and you're communicating over a public channel, which Eve has access to. You can still do it and have pretty much exactly the same prepared bits, and Eve knows nothing about those bits. Okay, so nobody knows what your secret number is, for example. Okay, so that's the idea. And the protocol starts like this. So Alice has, let's say, 4n qubits. And these qubits are either they're going to be pi 0, 0, which is going to be the zero state. Psi 1, 0, which is going to be the one state. Minus. And the preparation of these qubits depends on two. So this depending on two classical binary sequences A, K, and B, K. So K is going from 1 to 4, N. Okay, so we've got 4 N bits. And she encodes, so this is going to be phi, it's going to be the tensor over K of 1 AK BK. Okay, so she puts her A and Q bits together by looking at what is the entries in AK and BK. So if BK is 0, she uses the 0, 1 basis. And depending on whether and chooses 0 if obviously AK is 0, and 1 if AK is 1. Now this is the basis of the and if BK is 1, she uses the plus minus basis. So recall that this is the 0, 1 basis is the basis of the Z. So recall and a plus minus of the basis of the X. So Alice sends her 4 N qubits over a channel. So she sends this. So Alice sends the operator this, and this goes to the channel, and Bob receives. Let's say this curly E of what was set. Now, the curly E will come to a more precise definition of what that is in the next class, and that's going to be our launch pad to study error correction. But for the moment, you can just think, oh well, things might have changed. Okay, so things might have changed in these qubits here, and they might have changed firstly because in the communication, the environment will affect the channel itself, or will affect it with small errors. And secondly, because maybe Eve has been trying to have a look at it. Okay, so she's done some measurements to try and gain some information from these bits. Okay, so Barbara gets this string of qubits here. Now what he does is he chooses a random string himself. So Bob chooses a random primary sequence VK dash. And measures so this will be a predicted measurement. In the basis, in the Z basis. It measures the Z basis, so hold on. If B is 0, it's the Z basis, yes? And if B dash decay is 0, and the X basis, if B K dash is 1. Okay, so it's got a binary sequence, K is going from 1 to 4, for N again, he goes through them, and he measures in the Z basis. So you end up with a 0 or 1 measures, the projected measurement. And if you measure the X, you will end up with a plus or minus. Now, of course, he may well be measuring in a different basis to the one that Alice used to prepare the qubit for that particular qubit. So that may not be such a wise thing to do. So at this point, what happens is that Alice then publishes her sequence of Bs. Okay, so they now publishes her sequence of Bs, and they have a look and they see where the BKs were the same. If they were different, then they simply throw away those qubits. Okay, so Alice publishes the sequence BK. If BK is different from BK dash, then they discard okay, qubit. So they have 4 qubits, and every time in the sequence is different, they throw that qubit away. So they've got roughly 2 qubits left. Yeah, so they share now 2n roughly. Roughly 2n qubits. Which should be the same. They should be the same because Alice prepared them in a particular basis. Okay, so if the basis was 0, then she prepared them as 0, 1. It got sent through the channel, and then Bob is measured. If his BK is also 0, he's measured with respect to that 0, 1 basis, so it should be the same, unless a bit flip error has occurred. So suddenly, it's been put into superposition in which the probability that it measures 1 is now been amplified too much. So there should be this amplified so that it then accidentally collapses to 1. Or it may have been that Eve has been eavesdropping on this communication, and she has altered the bit, and for that reason, it's not the same. So what they do, so now they select n of the bits and see if they're the same. And then they have some kind of threshold. So they'll say if all but epsilon are the same, then they assume, they can assume n minus well, at least n minus, let's say, 2 epsilon of the remaining bits. Coincide. Okay, so they select n of the bits and they go, okay, well, if only a few of those are different, like very, very, very few of them, then probably Eve hasn't been messing about with communication. And the ones that we haven't publicly compared are going to be the same, all but very few of them. So now what we have is a situation where with these remaining qubits, as we have exactly the same qubits for both the same state. So that's, that could be a binary number, a number split binary, sorry, and that could be then used as the key for whatever crystal system they want to use. Now, this epsilon, of course, is not ideal. It's only a couple of them wrong, and we will see that if there are ways to get around that, to basically reduce that to 0. And one possibility is to encode at the beginning using an error correcting code, which is what we're going to do in the next section. So in that way, they can both then apply a recovery map and eliminate the errors. So then they will exactly have exactly the same qubits. Okay, so I think it kind of like motivates us nicely onto quantum error correction. Which is what we're going to do next. So that's the end of algorithms. Okay, so Bill says quantum error correction. 6.1 error quantum operations. So they call this quantum operations. So up until now, every system we've considered has been a closed quantum system. So up until now, all our quantum systems have been closed. But this is not the case in reality. We cannot have a closed system. In fact, if we, for example, want to make a measurement, then it's inevitably going to be some environment involvement in that measurement. So so in reality, we always have environment. And we call that interaction noise. And you probably heard that noise is a serious problem in quantum computation. So apart from the problems of trying to, and the superposition, probably not such a big problem. Polarized lights, you can put many quantum particles into superposition. C-naughts, more complicated. Start doing controlled operations on your qubits to entangle them. But a serious problem is noise. Okay, so to keep your quantum data relatively stable. Okay, so to not lose that information. For example, I mean, one of the problems being that if you entangle to, the entanglement will dissipate over time. So you'll have like dampening and things like this. So these are serious physical problems which have to be overcome if we are going to build a successful quantum computer. Well, in terms of the density matrix, let's get back to things. We have a row coming in, hitting our unitary operator, and our unitary operator then affected our density matrix in this way. Okay, so that will go like this, and now we're going to have, so this will be a closed system, and in an open system with some environment, you have rho coming in here, and then we have rho from the environment. Here, this is hitting a unitary operator, and what we're interested in is what's coming out here. Let's call it curve E rho. So to get this curve of rho here, we have to trace out, so we can recover. So we recover this rho by tracing out the environment. Okay, so recall we spent a fair bit of time doing partial traces, and this is what. Yeah? So now we're going to do partial traces of the environment, and that leaves us with, well, what our state is. Okay, so he gets hit by a unitary, which affects all the qubits effectively, and then we trace out over the environment to recover the density operator. So let's just recall, so for a composite system, A, B, tracing out over B means, so we would like it the sum over, what is that? J of J rho A B J where this J is an orthogonal basis for the B system. Okay, and we usually would write this as row A. And it's a bit weird because when you see this, you just think, oh well, it's pretty been bracketed by something, so then it's just a complex number. But of course, it's not in this case, right? It's because it's only affecting the B part of this. Okay, so it's worth having a look at, let's say, an example. Let's just see a simple example. Let's say A and B is 1, so let's say the A system and the B system both have one particle. Row A and B will be something like the sum over I, J, K, L of so C, I, J, K, L, I, J, K, L. Okay, so that would be a typical density operator, in fact, or an E operator. And if we trace out over the J, so let's say this is just using the computational basis, then row A is going to be sum over I and K of C, I, and J, C, I, J, K, J of I, R, I, K. Okay, so you sum up the conditions and you get this. Yeah, so let's do so that then a matrix acting on the K system. Okay, so yeah. Yeah, more generally, I mean, you could imagine just bracketing this with some vectors. So you could just have, because that's what bracket is. So let's just do that so it becomes hopefully clear. So if you just said, let's say B1 and B2. Our space in the B system, then you could do B1 row A, B, B2. That means something. So not checking out now, I'm just going to just so you could just take a C I J K L I K, and then you have B1 J L B2. And just trying to help you see, visualize that although this first looks just like you pre-programmed by a vector, that's true, but I mean it's not, it doesn't leave you now with a complex number, it leaves you the matrix on the A system. Yes. Okay, that's what I wanted to say. So now we've got a matrix here on the A system. Well, this operator, the A system. And in a specific case, when you do the partial trace, you take these to be the same, and then you sum them over in the following basis. Because otherwise it looks like what we're about to write down will look a little bit strange if you don't have that in the back of your head. Okay, so that was just things we kind of saw before. So as I said, so this we get by tracing of the environment of what did we have? We had U was being applied to rho tensor rho environment U data. Okay, so we had this from our little picture, and now we want to actually do that trace. Okay, so suppose we can suppose that. So first, let's think about rho environment. Rho environment, we can assume another thing we did way back when. Rho environment is just a density operator on the environment. Now we saw if the environment, let's say, has n qubits, we saw that we could extend it with another n qubits and purify any density operator into a pure state. Okay, so it was simply the Ket-Bra of some state on that system. So it doesn't really make any sense for us to, I mean, since we don't know how many qubits the environment has anyway, just double them and then assume that this is in fact a pure state. So we can assume that this is, let's say, the Ket-Bra of E0, and then extend this is an orthonormal basis for the environment. So now, let's just use K. So now I can do this partial trace, and that implies that this is the sum over K of EK U rho environment U dot EK. The rho environment we don't know. It's and as I say, now we just put an example for a reason, because we have to look at this and think what's actually going on here. These EKs, they're just on the environment system. And this is just on the environment system. So this is kind of a part here. This road doesn't make any difference, but then it is on here, and as well will be acted on by this U, which will be affected by this. So what we have here is this EKU E0, which, as we saw before in the last example, since these are both on the environment and this is on both systems, after, if you like, pre-multiplying by the EK and post-multiplying by the E0, this will be an operator then on the initial system, the system on which rho is defined. Okay, so this is really just EK rho EK down, where EK is EK U E0, an operator, so let's say EK is an operator on the principal system. I.e. where it grows. So hopefully that's kind of clear. That should be now clear from the previous example. No words? Okay. More or less. So this is something much nicer, something actually familiar. And we know something else. We know this is the density operator. The trace of this must be 1, which implies that the trace of the sum over k, ek, from is equal to 1. But we saw that the trace has the type of typical property, so this is just the trace of the sum of ek diagonal ek times rho, which we can then take out. So this is rho is equal to 1. For all density operators rho. No, I mean, I couldn't think of a nice way of showing the next line. It's tedious, but obviously if the trace of rho is 1, so for all density operators, just so that you can just stick in whichever one you like, and you always get 1 here, you better that this thing here has to be the identity. So this implies so it should all be looking terribly familiar. And indeed, because this is now looking like this is just the general condition like the set EK. So, and indeed that's the case. And we can like think of a physical interpretation of that. So if we go back and think, well, let's imagine that we measure. So suppose we measure in the basis this one after years of life. Well, it's no sort of very after years of life. Okay, so how would that be? Well, then we will get this. So before we apply U to our rho tensor environment, and then we measure it with respect to this optimal basis for the environment, and we'll get this with probability We get that. Yes, and then so we get this after the measurement, but then we need to trace out, so then tracing out of the environment. We will get the state, this without the again. Which was precisely the row UK with probability. And the probability, if you remember, would be the choice what you get left with, which is this. And you need to normalize, so normalizing we get rho k. So if the measurement ends up giving us k, then we'll get rho k, which would be this ek rho ek dagger divided by the probability, which is the trace ek rho ek dagger. And this all should look terribly familiar. It's exactly the same thing as you get when you do the measurements with respect to ek. Okay, so this is the, if you like, a physical interpretation of what we just saw, and we will get left in. So what does rho get left in? So if we get k in our measurement, then the operator gets left in this with this probability. So this was then pk. Let's call this pk. And then so the overall density operator describing the system after the measurement well, that's going to be the sum over k of pk times rho k. Okay, so we get, if you remember, that's in fact how we almost introduced density operators. It'll be with, if we don't know what the system is after we've done a measurement, but we know that it should be this rho k with this probability, so that allows us to describe the system after the measurement, even if we don't find out what the result is. So let's substitute what we know. Well, rho here is in fact ek rho ek dagger divided by the probability. So this is simply the sum over k of ek rho ek dagger, which is what we just proved before. Now, one final lemma, and then I'll call it a day, because next time we can really start with error correction, and I'll give an example of some EK. So we will start with the classical, the quantum analog of the classical bit town. So the final thing is very similar to something we saw before. So let us suppose that EY, EK, okay, are operations define the curly E and curly F. When we have curly E is equal to curly F, if and only if there exists unitary, and this UIJ such that and the proof, well, if we go back this way, then we know that we can just stick in this into the definition here. So we get the sum of EK, so let's say this is EI now, EI rho EI down is equal to the sum over I and J of U, I, J, F, J, rho, F, J, that of U, J. So this will be a different bar. And now the fact that it's unitary implies that U is unitary implies that this is the sum over J. Okay, so the usual tricks that we saw before, and indeed we saw this in an earlier theory. So this way is in fact similar to the proof of unitary freedom for decimal. Okay, so and if you want to see the proof, I'll have a look at this theorem 8.2 in but as I said, it's not too difficult. It's pretty much the same as we already saw for the density operators. Okay, so we will need this lemma when we look to proving one of the big theorems on quantum error correction. So we'll have two theorems which we might get to next time, which will show us that we really can correct our errors on a noisy quantum channel. And so incredibly important to know. And so that's going to be the kind of idea from now on. So we're going to look at error. We're going to look at these quantum operations, these curly E's, curly F's. Look at some examples. See how we can see how we can encode our quantum bit so as to protect against this noise by showing that we can find a recovery map which, when we then apply, restores our quantum system to how it was before. Okay. Then after we've talked about that, we will get on to fault tolerant stuff and everything. But I think we'll probably stop there for today. Let me stop there.